All right, welcome to Microcontrollers Review 2. So, today we're going to go over the stack, subroutines, and interrupts. And the right next digit to display subroutine. Okay. So all right, if you remember, in our MSP 430, we have a thing called the memory map. Where we have our okay. So this is our memory map. So this is the address for everything that's in the MSP 430. This top part up here belongs to the hardware. It's from the addresses 0 through 1FF, and from 200 to 3FFF, this is our RAM. From here to here is unused, and from here to here, C1000 to FFCO is our ROM. And at the very bottom, from FFCO to all Fs is our interrupt vector table. So, to start with, for the stack is in RAM, and it's built up from the bottom. And our variables are built down from the top of RAM. So, and to keep track of our stack, we have a stack pointer. And this is a register that holds the address for the top of stack. So we use the stack every time we want to save a variable temporarily or if we want to save a location and then go back to that location. So when we use subroutines, so when we call a function, we want to know where our last location was, so we can get back to the main loop or the main function after we're done with our subroutine. So when we do that, we save the value on the stack. So at the beginning, so in the beginning, at the top of our program, at it's not forward. Let me just double check. We have to have this line, move 400 into our stack pointer. And what this does is it says, have this stack pointer, and we're pointing to the very top of our stack to address 400. Now if you can see where I have this line drawn right here, 400 is actually unused. It's not used by the memory at all. The stack actually starts at 3FF. But starting it from address 400, it's like making sure that you have a good solid foundation, because you're not going to put anything into value 400. You're going to put the first value on top of that. But the stack pointer points to the very top of the stack. So just remember that 400 isn't actually used for anything. But when you put something onto the stack, either with like a push or a call command, or as we'll see later, an interrupt, it puts something on the stack pointer and then points to the new top address. So if, let's say, we push the value A, B, C, D, and hexadecimal, 0. We push this value onto the stack. Now, the MSP430 architecture is little endian. That means that this most significant byte would be right here. So if we push a word length instruction, we're going to have to use 2 memory spaces, because each memory space only holds 1 byte, and a word is 2 bytes long, or 16 bits. So you need to have a method to store both the bytes, and that can either be little endian or big endian. And this comes from the book Gulliver's Travels, and the argue, like, there's a little town called Lilliput full of little people, and they waged a holy war because some people wanted to eat their eggs from the big end and some wanted to eat their eggs from the little end. Very silly argument, and so it got this name that way. A little bit of trivia. But anyway, little endian. That means that the most significant bit goes to the more significant address. 3FF is larger than 3FE, so therefore it gets the most significant bit. A, B, C, D. And after this push instruction happens, we decrement the stack pointer from 400 to 3FE. So what a push does is it stores stuff on the stack and also decrements our stack pointer by 2. Even though we're saving only one value, and even if this push was instead of a word, was a byte, we would still use 2 bytes, and one would just be zeros, because that's how the architecture works. So even if we had, instead of push this value, I guess we could still have, so new value after we push that, suppose we push dot B 1, 2, then this would still use 2 bytes, but this one would just be padded with zeros. And we would again decrement the stack pointer by 2. Any questions? Do I have all you still understand? Okay. Pretty simple, right? Uh-huh.
So how does it distinguish if it's 12, 0, 0, 0, 0, 12?
So it distinguishes that by,
It's a byte, okay.
because it's a byte. So you know, because you're only using 1 byte when you push a byte, that you're just going to waste the other half of the word. Yeah?
Well, I was gonna say, because the .b command, is that worthless? Because it's gonna treat it like a word regardless. Right?
I wouldn't say it's worthless. It provides you, the programmer, context for what's going into it.
Okay.
So that then you know when you want to pop, you know that you're only going to get 8 bits here in wherever location, let's say R12, register 12. So the opposite of the push command, which puts stuff onto the stack, is the pop command. So say for example we have this pop byte, that would still take 2, even though it's a byte. Okay. So how a pop works is the push decrements the stack pointer, the pop increments the stack pointer, and then it puts whatever was in the stack into its destination. Both of these are only one operand instructions. So there's no source, you can only have one thing, like either the value or the location for like where to store it. What to store, and then for pop, like where to store. Questions? So let's say we have this pop B, R12. So that means that if we had this as our state of our stack and then we ran that line, we would take this value, put it into R12, and then this doesn't actually get erased. The stack pointer just points to the next one under it. So why don't we have to erase that? Why don't we have to set those to zeros? Anyone want to hazard a guess? Uh-huh.
Well, because it's when you push something back on, it'll just overwrite this.
Right, yeah. Yeah, so this is essentially lost. We don't have to waste time clearing that out because the next time we push something onto the stack, that value will be overwritten. Can anyone tell me what happens if you put too much on the stack? If your stack grows too much?
Stack Overflow.
Stack Overflow, the name of the greatest resource on the internet. Also is what happens if you push this value up past 200 or into your variables. Because like the real problem happens if you have the stack building up here, but you also have some variables. Like say you have a counter or like something that requires you to keep track of, like all your variables are important. Your stack can grow up into your variables if you don't keep track of it. That's why you shouldn't have subroutines within subroutines within subroutines, because at a certain point, It gets a little dangerous if you don't know what your stack is doing. Okay. Okay. So I think that's it for the basic stack. Any questions? Okay. So the next topic, building on it, don't have to erase all of it, are subroutines. Now, subroutines are what you call the things, like say, for example, the right next digit to display subroutine. Now, this subroutine is in your current project, I think the one that's due tonight, but you'll also use the same thing in your next few projects whenever you use the 4-digit display board, the 7-segment 4-digit display board. So make sure you understand it, and there will also be probably a couple questions on it on the test. But right now, just going to use that as an example of a subroutine. Now, how this works is you'll have your main loop or something, your main program, and you'll have a few instructions, setting up stuff, turning off the watchdog timer, setting the stack pointer to 400, a few other things for your code, and eventually you'll get to a call instruction where you call the label, the right next digit to display. And then there'll be some other instructions underneath that as you go, continue on. And then somewhere else in your code, after the main loop is all done and you like jump back to main loop so that it's a loop, you'll have your subroutine, the right next digit to display. So every time you reach an instruction that says call right next digit to display, you're going to pause in this location, save the address of the next instruction, and then go to this location in your code, the right next digit to display, where you're going to do some code. Take like the display value, calculate the indexing through the table, do all that stuff, write things out to the segment port to display the digit. And then at the bottom of that, there's going to be a ret instruction. What the ret instruction does is it returns you to the return address. Pretty simple. Now how this is handled is when call is called, it saves this address, the instruction right below it, onto the stack. So let's say right here, we call write, save the instruction, and let's say this address is like C1AB. That's about in the ballpark of what an address would be. So you would save this return address onto the stack, C1AB, decrement the stack pointer, because it needs to point to the top of the stack. And this decrementing is just a function of putting stuff on the stack. You don't decrement the stack pointer if you don't actually put stuff on the stack. So you point to there, and then the program counter is a register that controls what line you're executing. So it was just incrementing through here. But when you call when you call a function, it saves the value that it would have had onto the stack, and then loads this value into the program counter. So these labels that you see on the side, like main loop and right next digit to display, those are actually addresses. And the compiler treats them as addresses, so that when you compile your code, it goes through and replaces every label with the actual address. So the program counter will then go to whatever address is right here. Let's say that that's then like C412 or something like that. And then it will continue on ticking away 1.3, 1 whatever, as it goes down the list until it hits return. Now at return, when it hits this command, it pops the value that's off of stack and puts it into the program counter. Yes?
Excuse me, how do you get the value for the program counter again?
So the program counter, when you load up your program, it starts at C1000, or like at the very beginning of your code here. Now, the program that you write, all the moves, all the adds, all the jumps or whatever, they are encoded in instructions because everything is binary. So those binary, if you have a, let's see, a list file, yeah, I have one. Anyway, if you look at the disassembly of your program, you'll see that each line has an address. Now each instruction varies with length, so some addresses are like 4 bytes long and some are longer or shorter, just depending on how complex they are. So that means that the program counter won't just increment by 1, but it might increment by 4 here, 8 here, depending on the length of the instruction. But whenever you have your fetch, decode, execute loop, you know that? When you fetch it, it takes whatever's address is in here, and then like decodes it and executes it, and then it fetches the next one. So depending on the length of your address, it'll go to the beginning of the next instruction, and continue on from there. Does that make sense? So that's what program counter does. It just goes to the next instruction, the address of the next instruction, address of the next one, and continues on like that. And so by putting a value in here, like the value that was right next digit to display, it doesn't know that you just did a call, it just knows that that's the next thing to do. That's the next thing to decode and execute. And then fetch, decode, and execute, and fetch, decode, and execute, until you hit a return. Now what the return does is it takes the value on the top of stack, because you can't get stuff underneath the top of the stack, you can only access the top of the stack, that's what makes it a stack, right? Everyone's clear on that? Okay, don't need to go over data structures. So, takes the value on the top of stack and puts it back in the program counter. And then, of course, because it pops something off the stack, it increments by 2. Because it took that value and popped it off and put it into here in the program counter. So that means the next top stack is underneath there. So that's what a ret does. So then that means that the program counter can continue on to this line and go down to the next and next until you hit like another branch or until you jump back to the beginning. Any questions? Yes?
The stack is just a storage for the program counter to come back.
Yes.
Okay, to keep track of it.
Yes. So that's pretty great, right? The stack is useful because then you don't need to have like some other place to store the program counter, and you can go back to where you were and save like where you last jumped so you could go back. But occasionally you have issues because you as the assembly programmer also have access to stack. That means that when you push some value on the stack, that means that even if you already have your program counter at the top here, if you push a value on here, then it suddenly has a new value. And this program counter, this return address that you were storing on the stack, is suddenly not at the top of the stack. So what happens if you push something on the stack, but then return? Do you return to the right address? You return somewhere random, or wherever you had in here. You don't go back to where you want. So that's why, if you're using the stack, push and pop in a subroutine, always, always, always match up your pushes with your pops. Or else you run into problems, because the stack, there's only one stack for the entire programmer and architecture. Now some microcontrollers have more than one stack, like one that it's just used for jumping and like program operations, and one that the programmer can use, the assembly programmer, but not this one. This one's simple. There's only one stack. So that means that whenever you push, you also have to pop. After you're done. Any questions? So why would you want to use the stack? If using the stack is dangerous because you might end up somewhere where you don't want to be because of returning, why would you use it? Is there any use? Should you ever touch the stack? Yeah, it's still helpful. As long as you can use it correctly, it's still a helpful tool. Like, say you have some variable, but you don't want to go all the way out to memory to store it. Well, I guess it's still the same sort of memory. But you don't want to, you won't have to use it for many other things. Then you can quickly push it into a stack, do something, and then pop it off and do something more. If it's just like a one-time variable that you won't need. Also, if you're in a subroutine, so like the right next digit to display, it manipulates R15 because it needs to do that to do the right shifting and everything, because you can't really do that with variables very well. So before you go into this subroutine, maybe in your main program, you're already using R15 somewhere. So when you use a variable in a subroutine, it's good practice to, before you use it in a subroutine, to push it onto the stack. So the first instruction here would be push R15, and that way whatever you were doing up here that used R15 can be saved. And then after you're done with your instructions, you need to remember to pop R15 before you return. Yes?
So if R15 has some content, some value, and then you push it, before you pop it again, will it still have that value, or will it be moved?
Okay, well, let's have an instruction in our main loop. Let's say we move the value 2, 3, 4 into R15. But in our subroutine here, we want to use R15 to manipulate the display value. So what you do here is, because R15 is going to be used for stuff up here, when you call the right next digit to display, the first thing you should do is you should know what registers you're going to use in the subroutine. And you can store them on the stack by pushing them onto the stack, just as long as after you're done using the register, you pop the value off, return it to R15, and then you return from interrupt. So what this does is, let's clear our stack so we start fresh. So let's start fresh. So on this instruction, and let's have the registers here. Have the register R15, and it has some value. So I continue, go through my code. This probably does something if I'm using it up here. When I hit right next to display, I go to this subroutine. The thing with it saves the return address on the stack. That was my C1AB. And then here, this first instruction in my subroutine, I push R15 onto the stack. So what that does is it takes this value and puts it onto the stack. So now this points up here. To 3FCH. And then I'm going to move some value into here. So let's have that like, so some other random value. And then I'm going to manipulate my value. I'm going to do like my rotate less, my swap bytes, my indexing into the table, or whatever. So then at the end here, after I've done everything that I want to with this register R15, I pop the value that's on the top of the stack back into R15. So that means this gets erased. And this value that's on the top of the stack goes back in here. And that, of course, is moved to the new top of stack, and this is incremented. So that's what this instruction does. And then the next, yes?
You can continue.
Okay, and then the next instruction, the return from interrupt, then pops this off the stack again, puts the value in the program counter, and then like the program counter again points right here. And then we're done with this subroutine.
So my question was that push in the right, in the subroutine, is pretty much just to save whatever in that register that you're using above, and then to like put it back and continue where you were going.
Exactly. Okay. That way, because you only have a certain amount of registers, right? Mm-hmm. And it's conceivable that you could write a program that between all the subroutines and all like the loops, that all the registers are being used at least once. So this is a way for you to store a variable, so you don't actually have to make this like be a variable. So you don't have to write in your like definition of variables, have the temp var1, and then you're like, I don't know what this is used for. It's like only used one time. Like, so the way of using the stack is to prevent having like random garbage variables that you only need because you've run out of registers. Does that make sense?
I have one more question. When you push that R15, like in the subroutine, when you push it, what happens to R15? Like, is there nothing in R15 cleared out?
R15 continues to be as it was until you move the new value into it.
Okay.
Because actually, like clearing out everything, setting it to zeros, takes a whole other instruction. And you don't want to, like, one, degrade your D flip-flops by just using them too much that you don't need to, and two, you're not going to have to really clear out the value because those zeros that you would clear it to would never be used, because you would immediately then just move in the value that you want into that register.
Okay.
So it's pretty much just like being efficient. If you don't need to clear it out, then don't. In C programming, it's the difference between malloc and calloc. Malloc is super fast because you just have to allocate the memory. Calloc is slow because you have to allocate the memory and then clear everything. That takes time. Okay. Yes?
So the purpose for this is if we can manipulate the value in R15 without updating it, right? We can bring it back to what it was.
Yeah. So that means that because you use R15 in this subroutine, the value that you were manipulating doesn't escape. So that means that you could still use the same register here. And even here. So like say you wanted this value, like when you were like say you were using R15 for some counter or something, and then you wanted to increment R15 here and then jump depending on what was in the value of R15 or something. Then you could still use, like, it's a general purpose register. You can continue to use it wherever. Okay. Does that make sense? Any more questions? All right. Moving on to interrupts. Now, interrupts are like subroutines, only better, kind of. Tricky, probably. More tricky. Now the interrupts also use a stack, so I'm gonna leave that up there. Just a minute while I pull up my notes so that I can give you accurate information. Okay. Yeah. So, up to now, you've been using polling. So, when you press a button, you have to have in your main loop some way of saying, like, okay, so I pressed a button, I'm going to do my stuff, blink my LED, and then I'm going to come down here and check, is this button pressed? And then say, oh, it's not. Okay, I'm going to go back to the top. And then afterwards, is this button pressed? Oh, it's not. Or, yes, it is, and then go somewhere else. Now, that can be a little tricky, because sometimes you want to no, I want to detect when the button is pressed right now. I don't want to wait for a full on-off blink to test if the button is pressed. So, if you've run into timing issues, you're like, I have to wait for a full second before I can detect that the button is pressed. Interrupts are the tool for you, because interrupts happen within the tick that they're detected. So, how interrupts work is you can be running through lines of main code and maybe you have some something like this. So that you're running through the code and you test the button and then jump sometimes and then other times you don't. But while you're in here, you can't test if the button is pressed or anything. So what interrupts do is instead of this little code right here at the end inside your loop, instead moves it out to an interrupt vector routine. or interrupt service routine. Yeah, interrupt service routine. So how it does this is there's this, well, first there's this nifty table that you should all print out for your test. It's on page 11 of the device-specific guide, interrupt vector table. And this gives you the list of some addresses here and what causes the interrupt. So say if you have a timer that times out or you press a button, that's going to be on here. And that's going to be an address in this section of the memory map. So, and here. So, power up would be this bar. So like actually when power is turned on, it goes to this interrupt vector table, but when like port 1 ties into somewhere here, and timer A, and a lot of other things that tie into here. So how that works is you need to have an interrupt service routine, and that's a portion of the code that should execute whenever your button is pressed, or whenever your timer goes off, or whenever your interrupt happens. So let's move this over here. These are usually at the end of your main loop and subroutines by convention. Now let's call this one our port 1 ISR. So this is going to happen whenever we press a button or anything that's connected to port 1. It's port 1 and port 2. So what we need to do first, test. Which button, because you could have multiple buttons wired up to the same port, you need to test actually like which pin on the port, and okay, so this is a very simple interrupt service routine that when you press a button, you check if it's button 3. If it's not, you return from the interrupt. If it is, then you toggle the state of the flag, the pattern flag, and then you clear the interrupt flag, and then you go and return from interrupt. So what this does is basically if you press a button, it toggles an LED. And this could be used later to actually turn on or off the LED. So what happens is, now that you don't need to test the button in your code, you could just do other stuff. And then you could say like, oh, if, and then if we're using pattern state flag, then that you don't have to have your button test in your main loop. You can just do something and then the button will actually like determine whether you write out a 0 or a 1 here to your LED, like either turn it on or off, and that's handled just in this interrupt service routine. So that way this can just keep looping and looping whenever it wants. So the benefit of this is of course that you can do it whenever. The drawback of this is of course that you could do it, that these interrupts can happen whenever. So let's say that you're right here executing your code and you press the button and the MSP430 detects an interrupt. It says, hey, there's something here. So what it's going to do is it's going to finish executing this instruction and then it's going to save the return address. Remember, the next instruction down is the it's going to save this return address onto the stack. And it could still be the same. Let's actually make it a different address. Let's make it that. So it saves this on the stack, like a subroutine. But it also saves another thing on the stack, which is the status register. A status register is what contains bits like your 0 flag, negative, your carry, and like all that other stuff that's required for like knowing what to do with an operation. So, and the status register is also known as the context register. This is also saved on the stack when an interrupt happens. So let's call that. Let's say that some contents of the status register is saved on the stack. So when an interrupt happens, you save the program counter for the turn address as well as the status register. Now this one is 2 bytes long, and this one is 2 bytes long. So in saving these two things on the stack, you actually decrement the stack pointer by 4. So this isn't 400, it's now 3FC. And the reason why we have to save the status register when we're doing interrupts, instead of just saving the return address like when we call the function, is because we don't know when an interrupt will happen. We could be in the middle of a compare statement and then like jumping to somewhere else in the code. And for that, like if we have an interrupt happen right between our compare and our jump, we need to save like the carry or the 0 bit between our compare so we know which way to jump when we branch. So that's why this is saved. Does that make sense? Yes.
Value 9AF2, where did you get that value?
I made it up.
From the list file, where would we be able to retrieve that value?
This? I'm sorry. This is a made up value representing this value in here. Sorry. Yes.
So the status register is, it is 16 bits and not just 8?
Yes.
Okay.
But Yeah, I'm pretty sure it's 16 bits. I'm pretty sure it's 16 bits, but even if it wasn't, even if it was 8 bits, it would still take a whole word, 2 bytes, because that's how the stack works. You can't just save 1 byte on the stack, because that requires more flexibility than this architecture can actually handle. Yeah.
So for interrupts, do you have to like call an interrupt, or will it happen whether you call it or not? Like,
It will happen whether you call it or not. You need to set it up. Also at the beginning you have to enable interrupts. There's the command GEI, which is general interrupt enable, or you could enable interrupts for just the specific ports that you want.
so then there's a possibility that the interrupt will constantly happen when it's enabled. Because like if they can happen at any time, they can essentially constantly happen. Or no?
Can you rephrase?
It's like if you once you turn them on, and you said they can happen at any moment whether you call it or not. Can it like consistently always be happening? Like the interrupts, like after like every line, it'll just be an interrupt, and like or no?
If you set it up poorly, then yes.
Okay.
So it requires you to first set up, like if you're doing a timer interrupt, so that like you'll have the timer. Have you gone over timers? A tiny bit? Okay. I don't think it will be on your test. I think that's going to be on next one. So if you have a timer and you set it to interrupt every like millisecond or microsecond or something, then yes, you'll be triggered with the interrupt. But an interrupt cannot happen while it's already servicing an interrupt. So the first time that an interrupt happens, it'll have to go through this and check all of it and then return from interrupt. And then the interrupt will be triggered again and it will return from interrupt. It's also, while on your interrupt vector table, all the interrupts have priority from 31 highest to 0 to lowest. That means that if a timer interrupt happens at the exact same tick as a button is pressed, because the timer is listed above the ports, you're going to service the timer before you service the port. So that means that your interrupt service routine that handles what happens when the timer ticks or when the timer completes, that's going to happen, then it's going to exit, then it's going to take care of you pressing the button. Make sense? Okay. And that's why this table is, yes.
So the interrupt occurs, do you finish the line of code you're on, or
Yes.
it goes instantly?
Okay, so you finish the line that it's executing. So say I just fetched this instruction here, then I got the interrupt. It will finish decoding and executing, and then it will handle the interrupt. So what's actually going on is inside your little fetch, decode, execute loop, it's pulling all the interrupts. So instead of pulling in your main function, it actually pulls the interrupts every tick. Yes?
Are we supposed to be able to identify what status register we'd be holding when we put something onto the stack?
No, because there's a lot of things that influence the status register. Just know that the reason that you save it is because you could be in the middle of like a compare jump or like some sort of branching logic in which you need to like save, in which you would need to say, okay, so I subtracted this number from this number and got a 0. That means I branch over here. But before you could branch, an interrupt happened. So you need to save that, take care of the interrupt, go back and say, okay, which branch did I need to take? Ah, because I saved this, I'm able to know I need to take this branch and continue from there. Okay. All right. And I think the last thing to do, I think that covers interrupts. So, I guess I should say, when like a button is pressed or a timer ticks off, the hardware, like it's hardwired to go to one address on here. So like this address or this address, depending on the interrupt. So it's hardwired to look at this address and see that there's a value here. Stored in this address should be like the label port 1 ISR. And that tells it because all the labels are actually addresses, once the compiler is done with it, then it wants to go right here and execute the code here. So the things you have to do is you have to add the label of the interrupt service routine inside here at this address, and you can get that by at the bottom of your main code, you'll have a section where it says like org 0f e for x, and then you have to define word port 1 ISR, and then if you have another interrupt, then at the very bottom, end. So this is the very last thing in your code. Have to say org, then the address that's on the interrupt vector table, and that says go to here, and then define word port 1 ISR, which is the same label that you have for your interrupt service routine. So what that does is it stores this address right where it's going to look when an interrupt happens, and then for any other interrupts you use, you're going to have to do the same thing. I think always at the bottom you'll have an org 0FFF with reset, because that's the reset interrupt. So what happens if you press the reset button, or reset is called for anything. So it knows what to happen. Yes?
This thing says if the reset vector is at FFFF, it says the CPU goes into LPM4 immediately.
That's low power mode.
Okay. Is that what it usually is? Okay.
Yeah. So that means like, oh, you're not going to use anything, so going to go into the lowest power mode possible to keep everything barely functional so that your battery isn't drained. Okay. So let me see if this one has.
Olivia, I have a question. For the last bit, when you circle the port 1 ISR, so that stores the address for port 1 ISR in that?
Yes, so what these two lines of code do right here is it, actually, and then, like this is actually the address FE4X. So what these two lines of code are doing is in your memory map, it's saying that this address in your memory map, put the value or store the label port 1 ISR. Does that make sense? Okay. All right. I think that's everything for interrupts. Any last questions? Once, twice. All right. Okay. Also, for the test, I highly recommend printing out at least one of either Dr. Helm's sample code or your own project code. Usually the most recent, and that will just help you remember like the structure, and I don't know, it's usually helpful. You might not need it, but it's usually helpful to remember like the syntax or the addressing or something. Okay. So now let's cover the function of, whoops, where is Okay. Everyone's best friend, they're right next to display. Okay. So I'm going to write up some selections on this program. Okay. So and I don't think you should really bother to write this down because it's, like, I would much rather you print out one of your demo codes. Okay. So, all right. So, one more thing to do. Okay, so to set up for this, we have some constants, variable, and a table in program memory. So constants, these are all set in binary to different values. Because we're using a 7-segment display, we're using a 7-segment display. It's actually 8 segments because decimal point counts. So how this works is each of these segments are wired up to 1 pin on port 2. And it's active low, so when you write out a 0, it glows, and when you write out a 1, it doesn't glow. So what this does, what these constants do, is it defines like a pattern. So at the beginning here, we have segment A equals 0s, 1. And segment B, 0s, 1, 0. Now what this says is that it's saying that when we want segment A, or this segment on the top right here, to glow, we're going to write out a 1 in this position. Now that's great, but that you would actually get the inverse of this, and this continues all the way to the decimal point. So what we do here is we take this segment A, and we call it seg A-N for negative, and we inverse it. This little tilde sign inverses this pattern, so that instead we're writing out 1, 1, 1, 1, 1, 1, 1, 0. So on. So that's how we get it active low. So that way we can write it out so that we can see that, oh, these are the ones that we actually want lit up, but then it's active low so the computer understands what's going on. Another way to do this is right here, like for this instruction, when we want to write out the pattern that would result in a 1, because to write out with 7 segments, you would, actually I have another color, you would write out this segment and this segment, or B and C. So what this does, it has the tilde right here, and it just inverts this number right here with B and C highlighted to write out that. Same with 2, only in 2 we have A, B, not C, D, E, and G. So it'd be A, B, not C, D, E, and G, so we could get that 2. And so on. So this continues for all the numbers. Don't really actually need this portion, but that's just there so that you can see what's going on with the segments, because you're still learning. So that's cool. You can write out those numbers like that. What is segment pattern table doing with all these? So you can see that it's defining some of these labels right here that we defined right here. So that's just putting these values into a table like this. And the reason that it's at E1000 is because we need it in ROM. It's not actually part of our program, but it's like appended to the end because ROM can actually save values, unlike RAM, which as soon as you cycle power, it disappears. So that's why we have it in this segment pattern table. And display value, this is a word length, so 16 bits value that we're going to use to store our value that we want to display, our 4-digit number. So, at the beginning of right next digit to display, gonna abbreviate that because that's a long thing to write out. We push R15. Anyone remember why we do that? Yeah, I'm seeing that. Okay. Right. It's callback to earlier in the session. Okay. Then we compare okay. Now we also have a variable current digit position. We also compare the same thing to 1. So what this, and this continues for 2 and 3. So what this does is basically every time we enter right next digit, we want to increment which digit we write. Because we have 4 7-segment displays on our board, we want to write to 1, turn it off, write to the next, turn it off, write to the next, turn it off, write to the next, turn it off, go back to the beginning, and so we strobe the 4 lights so that at a fast enough rate so that it looks to our eyes that all of them are on. In fact, each one is just on for a few milliseconds, but that's fast enough because our eyes only see like so many frames per second, so it all looks like one number. And this saves pins so that we don't have to write out the whole number the entire time because that would take 3 more ports. So we save pins this way. Any questions on that?
When you say write to 0, what do you mean by that? Which?
Write 0? Okay. Getting ahead of me. So, quick question, does everyone understand multiplexing? That would be like write in one number, write the next, write the next, write the next. Okay, so don't have to go over that. Okay, so now, depending on what current digit position we're at, we then go to a little portion of the subroutine that controls what happens when we write a digit. So the first one, actually that doesn't need to have a line. Okay, so this is actually write dig 0. This is a label, and so that when we know that we're on position 0 or 4 digits, we want to do this little bit of code. So what we do first is we move FF to digit port. That's to clear the common. This just makes sure that the digit port is turned off, so that prevents ghosting. Then we move display value into R15. So that means that instead of having this in memory, we instead have it in a register. Registers are much, much easier to work with. In fact, you kind of have to work with them. Then we and R15 with 000F. Now, to understand what this does, let's look at our R15. Now R15 has our display value, what we want to display. Let's say at this point it's 33,000. I forgot the actual first number. But you'll want to display something like this at one point in time. Like your number plus some zeros or whatever. So what this does is this AND with R15. What's 3 and 0? 0. Yeah. Actually, let's change this to another number. 2, 3, 4. My favorite number. So 1 ANDed with 0, 0. 2 ANDed with 0 is 0. 3 ANDed with 0, 0. What's 4 ANDed with F? 4. I'm skipping a step and writing them all in binary. But if you remember, in binary, have like your truth table. So A, B, or and 0, 0, and 0. Remember this truth table? So that means that only when both bits are on do you continue to do the 1. So with ANDing 0, 0, 0, F, what you're essentially doing is selecting this bit. Because as you can see, these first few bits are now 0, and you only have this last one. Convenient. And then we add to R15. Add segment pattern table to R15. Segment pattern table, it's this thing. The segment pattern table is also a label. So it's a number. It's an address that actually points here in memory. So you can add that. So segment pattern table, because it's the first thing in here, it's actually the value of 8,000. Segment pattern table added with R15. Let's define it more bytes here. So now R15, well, at the end of this instruction, R15 contained the value 0004. At the end of this instruction, because we added segment pattern table, it ends with the value E1004. So, and then we have this line. So R15, what's in there looks like an address. And this line, at R15, does anyone remember what that does? It's an addressing mode. Yeah, so it treats the value of R15 as an address, not a constant. So what these two lines do, well actually what the whole line does, or what this whole little section of code does up until this point, is it takes a value, display value, like whatever number was in here, it isolates one of the digits, it then uses that digit to index through this table. So you start at E1000. This one is actually address E1001, E1002, E1003, E1004. So what this line does right here, is it selects the pattern for, actually it's going to be 4N, and that's a pattern like one of these that displays out this in this segment pattern table, and it writes that out to the segment port. So that's how it gets the actual like segments that you want to light up from the value in your display value. Does that make sense?
Another question. In the first line on the right, like move that B, what's the purpose of that?
So move.b f h to digit port. What that does is it just turns off all the lights so that, well, if you don't have this line, then if you write out something to this digit and then write out something to this next digit, there's like a brief amount of time where you show the old digit on the new one, and that's called ghosting. And you see it as like a very faint little glow of the old number. Don't want that, doesn't look pretty. So that's what this line does. This one turns off ghosting.
So it clears whatever was displayed, whatever was turned on?
Yes. Because it's active low, if you're writing out ones, you're turning them off. That's why we do this little tilde right here to reverse the bits.
So the digit port, not the setup port?
So how this happens, or what's going on here, is you have digit port and segment port are port 1 and port 2. Digit port has 4 pins that connect which digit you're lighting up. There's actually a 5th one that controls the semicolon and temperature point. And segment port is what's in charge of all these. So segment port controls the 8 numbers that light this up. Digit port controls which number you're lighting up at a time. So right here, that's just clearing this, so it's turning off all the lights all at once. Then the end of here, running out of board here. Digit 0 N. And this is the line that turns on digit 0. Jump. Done. So that's how you turn on one number. Now, writing digit 0 is the easiest number because you're just masking out this last one. But, any questions on this? Yes.
Why are you ending it together with 000F?
Right here?
Yeah.
So this is a mask. This is how we get from, say, our display value at the top of this. One, two, three, 4. What the AND does is it masks out the 1, 2, and 3, so it only retains the 4.
Why F though?
Why F?
Yeah.
So F, anything ANDed with, well, remember your truth table for AND? So a 0 and a 0, ANDed is a 0, 0 0 and 1 is a 0, 1 and 0 is a 0, a 1 and a 1 is a 1. So what happens when you have binary 4 and binary F, and you and these together, you get 4. See how that works? And any number like up here, like it could be a 4, it could be an A, it could be a 1, whatever number you have here, if you and it with all ones, it's going to be itself. And anything anded with a 0 is going to be a 0. So that way, you're able to select just one portion of the word length display value if you just want 4 bits of it. How you use the other, let's go to instead write digit 1. There's just a few differences between this and right digit 0. Okay, you're still going to have that ghosting line.